In this video, we're talking about how heat moves from one place to another, and there are three essential mechanisms. The first that we'll talk about is conduction. Thermal conduction, again, stems from energy sharing collisions that happen across a particular barrier between two surfaces. And we can describe the rate at which heat flows, which also is the same thing as power, as being directly proportional to the surface area that the two materials are in contact with each other, and the temperature difference. So larger temperature difference is going to be a greater heat flow, but inversely dependent on the distance over which that exchange can happen over the thickness through that mixing goes, conducts itself. And then this is all proportional to the material itself. So we saw previously that the material could be reflected by specific heat capacity. And in this case, the property of the material is represented by K, which is thermal conductivity. So here are a list of different thermal conductivities, and they're presented in both kcals per time and distance in degrees C, or in joules. And we can see that metals are the most conductive, and that's because of the same reason that they're good conductors of electricity. And they have valence electrons that move quite easily and easily participate in these energy sharing collisions. Then if we take a look at other materials, it seems like the less dense the material, the poorer its conductivity. And you can see that air is actually the least conductive of all. But when we do insulation, we don't just leave an air gap. And that's because of a different form of heat transfer, which is convection. Now, before we move on and talk about convection, we will just pause for a minute and think about this thing that we know as R values. And in home construction, R values are very important. And the other important thing about R values is that they add. So if we take a look at the examples that are presented to us, we have fiberglass insulation that's 4 inches thick and it has an R value of 12. Now, if that fiberglass is sheathed by plywood, half-inch plywood, then it would add 0.6 R values. And so that would build the R value up to 12.6. If the outside is brick, then we would add on another piece. But you can see that glass, brick, plywood, not really great insulators. And fiberglass, if you decided that you were going to add some, if your walls were 6 inches thick instead, then your R value would go up to 18. So R values simply add, which is very handy. You also notice that the units for R value are in imperial units. Feet squared, hours, degrees Fahrenheit per BTU. So that when you solve for Q over T, the units for that answer are going to be BTUs per hour. But fortunately, we know how to use unit converters on various websites in order to convert to joules per second or whatever it is that we need. Now, the key element of convection is that convection needs gravity. In these energy sharing collisions, faster collisions require a little bit more space. And so that means that warmer parts of the material typically are less dense than the cooler parts of the material. And gravity is going to try and drive that upward while the denser stuff settles downward. In the picture on the right, we can see that heating a house in this particular example, which is forced hot water. And in Burlington, there are lots of places that still have forced hot water. It's not a bad way of heating a home, but it does count on a couple of things. So in the furnace, we have a hot zone where there is contact, the firebox is in contact with the water reservoir, and so that's heat by conduction. Then hot water is driven up, and it could be forced, or it could be just gravity fed too. But that's not doesn't heat as evenly, and so we often have forced hot water. And so the water will go up into a radiator, and then the job of the radiator is again to make use of conduction and to warm the air around it. But then that warm air rises and brings cooler air in contact with the radiator, and it continues. So you'll see a lot of old style radiators in some older apartments in Burlington, and typically if they have any air trapped in them, they'll make a pretty loud thumping noise. So sometimes the air will have to get bled off. Heat transfer by radiation. This is electromagnetic radiation. Oh, so, or thermal radiation is another way that it's described. And this is extremely common. So if you've ever had a chance to put your hands in front of a warm wood stove or a campfire or something like that, you were experiencing heat transfer by radiation. But almost all things radiate heat in some way. And this can happen through infrared radiation. So thermal cameras can be used to scan houses, or scan for humans for that matter, but scan houses to look for places where they're losing heat. Now, when objects glow, like a glowing wood stove, which is probably a little too hot, but we can see that the energy that's rated off, or at least the rate at which the energy is rated off, is proportional to the temperature raised to the fourth power. And we have a couple of key constants here. First of all, there's E, which is emissivity. It's a number between 0 and 1, which tells us about that material and how well it absorbs or gives off radiation. So an emissivity close to 0 means that it doesn't absorb heat very well at all, and it doesn't radiate it off very well. And objects that are dark colored have an emissivity closer to 0. And the Stefan Boltzmann constant is simply a proportionality symbol that makes things work out. Now, I see that we have a link to sea ice time lapse. So we have one consequence for climate change and global warming is that we are losing the polar ice caps. In particular, the one in the North Pole is under the greatest threat because there's no continent underneath it. And as the planet warms and there's less polar ice cap in the Arctic region, especially during the summer, then we go from sea ice to seawater. And the emissivity for ice is very, very low, around 0.05, but the emissivity for seawater is about 0.96. So that means that when the Arctic ice cap loses its ice cover, it absorbs energy from the sun 20 times better. So unfortunately, that is a feedback loop that favors the complete loss of the northern ice cap. So quantifying the radiation that we get from the sun can be used in, say, assessing what solar panels are going to be able to produce. So we have something called the solar constant, which is 1,000 watts per square meter. And that's essentially what sunlight looks like when it comes to us. And then our object could either be reflecting the light or absorbing it. In the case of solar panels, we hope it all gets absorbed. And in that case, that would be an emissivity of 1. And then also the cross-sectional area we're talking about, and then also the angle that the light makes with the surface area that we're talking about. So you can see in this case, theta is measured from the vertical, and that's why we use cosine. So if theta was equal to 0, the sunlight would be coming perpendicular to the area. And if it was 90 degrees, then it wouldn't be encountering or delivering any radiation to that surface. So, of course, our seasons in the northern hemisphere are different than in the southern hemisphere, and the cosine effect is responsible for the seasons, of course, and also how much thermal warming and also the viability of solar panels in different parts of our planet. So the total amount of solar radiation we see in this diagram, you can see is coming in essentially parallel, and that's because the sun is so much bigger than the Earth. So the sun rays do essentially come in parallel. But based on the tilt of the Earth's axis in its orbit, we can have more radiation hitting the northern hemisphere or the southern hemisphere or equal amounts. So in the next video, we're going to take a look at applying a couple of these examples in problem solving.